So I'll say here, this is a video lesson on a Riemann sum using midpoint rectangles. I'm going to begin by drawing a function that we might want to estimate the area under the curve of, and this function will have a sharp curve. We may be asked to estimate the area between A and B under this curve that we will call F. And rather than present dividing this curve up into a whole bunch of rectangles, I'm going to focus on a representative rectangle. We're going to just visualize one of them to talk about the difference between a left-hand estimate, a right-hand, and a midpoint estimate. So if I have one rectangle between these 2 points, and if I use the left point of these two to determine the height of the rectangle, the representative rectangle could look like this. And we know that in this case, the rectangle is going to be an underestimate because the rectangle's area is less than the area under the curve. A right-hand rectangle would use the right point for the height of the rectangle, and in this presentation, it's the right-hand rectangle which will be an overestimate by the amount that the rectangle is greater than the actual area. So a midpoint rectangle, if this was the difference between these two locations, what we call the change in x, and if we're going to use a Riemann sum, then these delta x's have to be all the same for all of the rectangles or shapes that we use. A midpoint rectangle is then found by taking the domain location that is exactly in between the left and the right sides. And right in the middle, if we use that function value as the height of a rectangle, then we can see that in this case, part of the rectangle is going to be an overestimate by the amount of area that is above the actual area, and part of the rectangle's height is going to be an underestimate because we can see that the curve goes above the rectangle height in that case. And if we have a portion of the error, both positive and negative, then that amount of error cancels out. And the true error or difference between the rectangle area and the actual area is then the difference between these two regions, which is going to be much smaller of an error than the left and the right. So midpoint rectangle method is most often a better estimate. But just like using trapezoids, we're not going to necessarily know if it's an under or over estimate. So the left and rights to give us a range, even though crude, is still very often good information. How do we create the Riemann sum for these three? Well, from the past, we know that the left-hand rectangle method, abbreviated LHR, as a Riemann sum in general terms, starts with a k-value of 0 and goes up to 1 less than the number of rectangles that you're going to use. A k-value of 0 means that we are not going to go, we're going to start by not going over by any delta x's. We're starting at A. So in the expression, k represents the number, the integer number of delta x's that we will be going over to find all the various heights that we need to take the sum. Starting with a k-value of 0, we don't start by going over any delta x's in the beginning. The expression then for the sigma, or the argument of sigma, is delta x, which represents the base of every rectangle, times the heights of those rectangles, which come from the function values, but only at those locations that begin with A, and then add a certain number of delta x, k, where k is the indexing variable. It's the thing that changes. Now in the right-hand rectangle, we could abbreviate that RHR. What we're changing is not the argument. The argument of sigma is still delta x f a plus delta x k. But we change the index. We change the index by starting at 1 and going up to n number of rectangles. Where we're starting is 1 delta x over. That's how we get from the first left-hand side to the right of it, by adding a delta x at the very beginning. And how do we add that delta x at the very beginning? By starting with a k value of 1. So we're literally mathematically adding 1 of the delta x's. Now I've spent a lot of time focusing on this starting point because getting the midpoint rectangles, or MPR to a common abbreviation, we're going to modify where we start. We're still going to use sigma. We're going to begin with a k value of 0 and go up to n minus 1, just like the left-hand rectangles. The argument is still going to multiply delta x as the base, and we're still going to get our heights from the function. But our beginning is going to change. How? Instead of starting at A, where we have a k value of 0, we're going to start halfway over half of a delta x. And this location here, the middle, is going to be the first function value that we want to find the height with. So how do we get there? We still need to start at A, and we're still going to go over by delta x k's, but we need to add, to change that A location to halfway across, we need to add half of a delta x. Once we add half of a delta x and start in the middle, then adding delta x's from that middle point will continue to get middle locations all the way through in the algorithm. So we show that in the expression in the argument of sigma. This inclusion here is all that is necessary to turn a left-hand rectangle estimate into a midpoint rectangle estimate. For example, we could be given notation, find the area under the function x squared from 1 to 4, and then also include the instruction to do a 6 midpoint rectangle estimate. With this information, for sigma, we're going to need to know what delta x is. That is the upper bound minus the lower bound divided by n, or 4 minus 1 over 6, which is 3 over 6, or reduces to 1/2. We have our a value, or the lower bound of 1. We know that the function that we're going to use is parent quadratic, x squared. And of course, n number of rectangles is 6. Now with this information, I can create the sigma notation for the estimate. Start with a k value of 0, go up to 1 less rectangles, then multiply by the base and the height, where the base is delta x, 1/2, and the heights are going to be the squaring function, where we put a plus delta xk plus half of delta x in, and that is 1, plus delta x is a half times k is k over 2, plus then half of delta x. If delta x is a half, then we have to add a quarter. Adding that extra quarter means that from our beginning location, we're going halfway of a delta x in order to find our beginning, which will then find the halfways every time afterwards.